In this session, we'll continue our analysis of the Subway restaurant. We're going to be zooming in on the labor productivity of the employees at Subway. Specifically, we want to have some performance measures that we can track, telling us how much productivity is going on in the store. For this, I will first introduce three new variables: the labor content, the cycle time, and the idle time. Based on these three variables, I'll then introduce two new performance measures. They'll be called the average labor utilization and the cost of direct labor. Let me formalize the concept of line balancing. Before we do this though, let's review some basic definitions. We define the capacity of a resource as a ratio between m, the number of people or machines at this resource, divided by the processing time. We define the process capacity as the minimum of the capacities of the various resources in the process, and then the flow rate as the minimum between demand and capacity. Finally, we previously defined the utilization as the ratio between flow rate and capacity. Now consider the following process. Imagine I have 4 stations, each staffed with 1 worker. The processing times are shown in this picture here in green. You see that station 1 has a shorter processing time than station 4. Consequently, given that there is 1 worker at each of these stations, we're going to see that station 4 is our bottleneck. Given that station 4 is slower than stations 1, 2, and 3, stations 1, 2, and 3 have some slack time relative to our bottleneck. We refer to this slack time as idle time. To formally figure out how much red time, how much idle time these 3 steps have, let me introduce the concept of a cycle time. The cycle time is simply 1 over the flow rate. The cycle time is like measuring at the end of the process how much time passes between the completion of 2 subsequent units. For example, I might say that this process is operating on a 115-second cycle. That means that there is a process unit leaving every 115 seconds. Next, we define the direct labor content as a sum of the processing times. This is simply in the previous picture the sum of the green bars. Next, we define for each resource the idle time as the difference between the cycle time and the processing time. So the idle time for the first resource is exactly this difference here. We can add that idle time up across all resources to get the total red in this picture, the total amount of idle time. We can then define the average labor utilization in the process as a ratio between the labor content, remember the sum of the processing time, and the labor content plus all the direct idle time. The labor content really measures how much green there is in the process versus the labor content plus the direct idle time, the denominator here in this definition, captures how much time I have to be paying for in total, which is the labor content plus the idle time. Finally, we define the cost of direct labor as a ratio between the total wages per unit of time, for example, 4 workers times the hourly wage rate, divided by the flow rate per unit of time. To practice our new definitions, consider the following example. This here is a machine paste line consisting of 6 workers working in sequence. It is a machine paste line because you notice there are no buffers between the stations, meaning that these 6 workers have to work exactly at the same pace. Though the first station has a shorter activity time and thus excess capacity, that station cannot run ahead. The entire process will be paced by the slowest step that we will see in a moment is the station number 5. Now let's practice our definitions. We have the processing times over here in this first row. Next, we can compute the capacity as simply as 1 over the processing times. For the first one, let me put the units along here. So this is units per minute. 1 over 5, 1 over 2, 1 over 3, 1 over 6, 1 over 2. We can apply our definition of the bottleneck and say that the step with the lowest capacity is the bottleneck. That makes station 5 indeed the bottleneck. Assuming there is enough demand for this process, we're going to have a flow rate that is going to be 1 unit every 6 minutes, which corresponds to a 6 unit per minute. Or alternatively, we could say that this process is producing 10 units per hour. We can then define the cycle time of the process as 6 minutes between units, which I hope is intuitive because that is exactly the activity time that we have here at the bottleneck. Next, we can compute the idle time at each of the resources as the difference between the cycle time and the processing time. That would be 3 minutes here, 1 minute here, 4 minutes here, 3 minutes here, 0 minutes here, and 4 minutes here. We'll then define the labor content as the sum of the processing times, which is 3 plus 5 plus 2 plus 3 plus 6 plus 2, which makes a total of 21 minutes per unit. The total idle time across all units is 3 plus 1 plus 4 plus 3 plus 4, which is 15 minutes. We can then define the average labor utilization as 21 minutes labor content divided by 21 plus 15, which is the average utilization in this process. We can also compute the cost of direct labor in this process as the ratio between the wages and the flow rate. Say for sake of argument, each of my workers here is making $20 per hour. So my wages are 6 workers times $20 per hour divided by the flow rate, which we said was 10 units per hour. This gives me a direct cost of labor of $12 per unit. Let me take these calculations that are arguably somewhat messy right now and plug them over into my Excel spreadsheet where you can read them more clearly. Alright, let's review these calculations in Excel. So the first thing that we're going to do is we compute the capacity of each of the resources as 1 divided by the corresponding processing times. This is now expressed in units per minute. Next, we're going to compute the process capacity as the minimum of the individual capacity levels, which determines that indeed station 5 is as we expected, the bottleneck. We can then compute the flow rate as the minimum between demand and capacity. We assumed here that there was sufficient demand, and so the flow rate is given by the process capacity. We can compute then the cycle time as 1 divided by the flow rate, which is telling us that we are making a unit every 6 minutes. This allows me then to compute the idle time at each of the resources. For that, I'm going to take the cycle time and I'm going to subtract the processing time at each of the resources. With this in mind, I can compute a total idle time, which we confirm to be 15 minutes. Now, is 15 minutes a lot of idle time or not? This is really hard to judge. And so we compare this number to the total labor content in the process, which we previously defined as the sum of the activity times. I can then compute my labor utilization as the ratio between the labor content and the labor content plus the idle time. 58% is my average labor utilization in the process. Note the following. Let's quickly compute the utilization of each of the 6 steps in the process. Utilization, remember, is the flow rate divided by the capacity. You notice 100% utilization at the bottleneck, which I hope is intuitive. We can then go ahead and we can average the utilization of the 6 resources, and voila, we also see a 58.3%. At the risk of repeating myself, let's go back to the subway example and revisit the previous calculations that we did. Now extend these calculations by the following. The cycle time is computed as follows. We said that there were 60 customers per hour. That means every 60 seconds, since there are 3,600 seconds in the hour, every 60 seconds we have a unit of demand. The cycle time thus is 60 seconds. We then can compute the idle time of the various resources as the difference between the cycle time and the processing times. We can sum up the total idle time and find it to be 60 seconds. This is really 60 seconds per sandwich. The next thing that we can do is we can compute the labor content, which is also expressed per sandwich as the sum of the processing times. With those two pieces of information, I can compute the labor utilization then as the ratio between the labor content and the labor content plus the idle time. This is 66.6%. Notice, by the way, that as before, this is also exactly the average of the individually computed utilizations. I often get asked why we make such a big deal out of labor cost. If you analyze the P&L from big corporations and manufacturing these days, you actually see relatively little labor cost on their P&Ls. My colleague from MIT, Dan Whitney, has done a very interesting analysis in the automotive industry that addresses this matter. If you analyze the profit and loss statements of an automotive company, you indeed see that the vast majority of the money is spent on purchasing. About 70% of the total cost incurred at Daimler Chrysler at that point was spent on purchasing. This is very similar if you look at electronics makers, who are also going to spend 70 to 80% of their total cost on procuring items such as disk drives and microprocessors. Now, the labor cost here, if you look at things related to assembly labor and maybe inventory cost, is just a tiny fraction. However, this is misleading. This is hiding the fact that your purchasing costs are the total cost of your supplier, and that includes their labor cost. So you see that if you look at your labor cost plus what the supplier is spending, actually labor is becoming a bigger component. If you're rolling this up throughout the value chain, you actually notice that a very significant part of the item in a vehicle is spent on assembly labor. What the recent trends towards relying more on suppliers and emphasizing purchasing more has done to the P&L statements, it has been hiding labor costs from our books, shifting the labor costs to our suppliers. However, they haven't disappeared. They're still in the value chain. And what top-notch manufacturing companies do is working closely with their suppliers to further reduce these labor costs, independent on which books they are listed. In this session, we introduced two measures of labor productivity. We talked about labor utilization, and we talked about the cost of direct labor. Neither of these two measures is good or bad by itself. Labor utilization is more a measure of line balance. However, we might have a perfectly balanced line of very expensive workers, so a process could be very unproductive, but have a perfect labor utilization. The cost of direct labor is capturing another angle of that productivity. It captures the wages that we have, as well as the productivity of the employees in terms of how many units of output that they can create relative to their wages. We've also seen how firms can hide labor from their books by relying more on their suppliers, by outsourcing ultimately the labor. If you think about Apple and Foxconn, Apple might only have 60 or 70,000 employees, but Foxconn as their main supplier has over 1 million. So just saying that based on the financials at Apple, we don't see a lot of manufacturing labor there, and thus manufacturing labor is not important for Apple computers, is really misleading. Labor productivity on your books, on your supplier's books, is absolutely critical in operations. For this reason, we'll revisit many aspects of labor productivity as we'll talk about the productivity module in a week from now.